There we go. Okay, so number nine. Number nine. Okay, on number nine, we have f of x equals x minus 2 sine of x. And we're looking at this specifically from 0 to 3 pi. Okay, so that's restricting a little bit what we've got. We have to find the first derivative, and so when we find the first derivative here, our f prime of x is just going to be 1 minus 2 cosine of x. Okay, since we are looking for intervals where it's increasing and decreasing, we're looking for minimum points, we're looking for maximum points, we need to find critical numbers. Okay, our very first step in this process every time, take the derivative, figure out where the derivative is 0, where the derivative is undefined. Is cosine of x ever undefined? No, I can put anything in and it's going to spit a value out. There's no asymptotes with cosine of x. It is what it is, right? So I'm going to say here 0 equals 1 minus 2 cosine of x. And my goal here is we're trying to identify any critical numbers, critical values, critical points, critical stuff. Okay? Subtract 1. Divide by negative 2. Right? So I take 1 away. I divide by negative 2. And I am thinking about all of the places where cosine of x is equal to 1/2. Okay? So where does cosine of x equal 1/2? Okay? Cosine of x, if I'm thinking about that graph. Right? Going up and down, up and down. This right here is 2 pi. This right here is 3 pi. Okay? So this is like our cutoff point for our graph. Okay? We're only looking at values between 0 and 3 pi. That's what it says in the problem. Now, we want to figure out where cosine is 1/2. Okay? So if I think about 1/2 as being a line right here, there are going to be 3 locations on this interval where cosine of x is equal to 1/2. Are we in agreement there?
Yeah.
Okay. Where's the first one? Pi over 3? Okay. So at pi over 3, cosine pi over 3 is 1/2, 60 degrees. Okay? This point over here is just pi over 3 on the next bump over, right? Cosine's periodic, so this point is going to be pi over 3 plus 2 pi. That's going to be this point here. Okay? This one, okay, with cosine, pi over 3 is going to get us 1/2. Negative pi over 3 is also getting us 1/2. This point is 2 pi plus negative pi over 3, or just 5 pi over 3. So those are the 2 points on the unit circle, pi over 3 and 5 pi over 3. And then we've got this extra one, which is 7 pi over 3. There, okay? So the three critical numbers between 0 and 3 pi are pi over 3, 5 pi over 3, 7 pi over 3.
What is 7 pi over 3 not at 3 pi?
3 pi is 9 pi over 3. So we're not quite to that yet, okay? Now, I'm going to take these points. I'm going to take the 3 critical numbers. And put them on a number line. We're going to be patient. Just everybody understand how I'm getting the critical numbers. We understand that it's where the derivative is 0. Got that part down. Are we somewhat confident in how I'm figuring out what those numbers are with the exact values? You're thinking like back to unit circle trig, places where cosine is equal to that. Okay, so if I'm looking at my number line is a little bit different than it was yesterday because I have this interval, right? So I'm going from 0 to 3 pi. And I'm going to mark off these locations, right? So I've got pi over 3. I've got 5 pi over 3. I've got 7 pi over 3, not drawn to scale. Okay? So I have 1, 2, 3, 4 intervals to check. I got 4 intervals to check to see whether I have a positive interval or a negative interval. Now, use the little graph that I drew to help us out here, right? So like our derivative is 1 minus 2 cosine of x, right? So we got to think about this here. If I take values between 0 and pi over 3, what would be a good number to pick between 0 and pi over 3? Pi over 4, pi over 6, those are only real options, right? So how about like pi over 4? Okay, if I choose pi over 4 in this interval, I'm going to try and figure out what f prime of pi over 4 is equal to. Okay, remember, I don't need to know what it is as an exact value or anything. I just need to know if it's positive or negative. Okay, I'm going to take 1 minus 2 times the cosine of pi over 4. I'm taking pi over 4 and I'm putting it into the derivative. Okay, so cosine pi over 4, square root of 2 over 2. The 2's cancel out. I'm left with 1 minus the square root of 2. Is that positive or negative? Which one's bigger there, 1 or the square root of 2? Negative, because square root of 2 is bigger, right? Square root of 2 is bigger than 1. So this is negative. Okay, so my first interval there is negative. My first interval there is negative. Okay, probably between pi over 3 and 5 pi over 3, I'm going to choose pi. Pi seems like a very wise choice, right? Or I could maybe even choose a wiser one of like pi over 2, right? Pi over 2 is going to make this 0. So if I do f prime of pi over 2, I'm going to get 1 minus 2 times cosine pi over 2. That's just 1 minus 0. It's 1. That's a positive interval. Okay, whatever point that I'm taking between the 2 points that I have as my critical number, whatever point I choose to take, I'm taking it and I'm putting it into the derivative. I'm determining whether it's a positive interval or a negative interval. Okay, between 5 pi over 3 and 7 pi over 3, 2 pi. 2 pi is a great point to take. F prime of 2 pi. F prime of 2 pi. I got 1 minus 2 cosine of 2 pi. Cosine of 2 pi is 1. So we're looking at 1 minus 2, negative number. Negative. Okay, I got that. Okay, and then the last one, you know, like, okay, so I'm going from 7 pi over 3 to 3 pi. This deal is, it's periodic, right? So going from 7 pi to 3 is the same as like going from pi over 3 here. This one is also going to be positive. Okay? If I put in like 2 pi plus pi over 2, I'm going to be on this region here. It's the same result. Okay? So I've got a negative, a positive, a negative, and a positive. That is a lot of work to get to the point where we can even have a conversation about what is the derivative telling us here. Okay? So this is telling me between 0 and 3 pi. Negative derivative. My graph is going down. Positive derivative, my graph of f of x is going up. Negative derivative, it's going down. Positive derivative, it's going up. So if I'm trying to answer the question, where is this function increasing? It is increasing from pi over 3 to 5 pi over 3. It's also increasing from 7 pi over 3 up to 3 pi. And I'm going to end at 3 pi because that's where they tell me to end the interval. Okay? It's increasing on the places where f prime is positive. F is increasing when f prime is positive. Okay? F is decreasing on two intervals from 0 to pi over 3, and also from 5 pi over 3 to 7 pi over 3. Okay, it's decreasing when f prime is negative. Okay, now, what is going on at pi over 3? Talked about this yesterday. Derivatives going from negative to positive. We know that we have a relative what? Min. Okay, going from negative to positive. So at that point, my graph is going down. It's 0, and then it goes back up. Okay, so we have a relative min at pi over 3. Where else do we have a relative min? Where else is it switching from negative to positive? 7 pi over 3, okay? We have a relative max. We have a relative max when it's switching from positive to negative. So 5 pi over 3. Anywhere else? Can we say 3 pi? No, because we don't know what's going on the other side there, right? Okay? So min, max, mid. Okay? We're still working on the same problem. Okay? Because now we want to try and find concavity. It's like a whole other problem. This is ridiculous. Okay? There's like 87 parts of this problem. So I gotta find the derivative. I gotta find critical numbers, plot out those points. Test out a point on each interval to determine if it's a positive interval or a negative interval. The good thing is after we do one with trig in it, the other one should seem much better, right? So now I'm going back up. Now I got some second derivative work to do. So I'm going to go over here. My f prime of x is 1 minus 2 cosine of x. That means f double prime is 2 sine of x. Okay, now just the advantage of not having that 1 in there makes this a much easier prospect to deal with. Because a sine wave, I kind of know what that is. I know where the zeros are. It's not as bad. All right, so I'm going to look at the graph of f double prime. Okay, f double prime is 2 sine of x. Why am I going to do the graph? Because sometimes when I'm talking trig, it's easier to talk about the graph than the equation. Okay, sine wave looks like this. It goes up, it goes down. I'm at 2 pi. It goes up, comes back down. This is 3 pi right here. This is pi. This is 2 pi. Okay, so if I'm talking about critical numbers, okay, it's not really critical numbers, but if I'm talking about places where the second derivative is changing sign, and I'm looking at a number line for the second derivative, the important points are pi and 2 pi. Also, because this is the whole graph, I know that sine of x is positive. Sine of x is positive between 0 and pi. I know it's positive without checking any points because I can see it on the graph. I know between pi and 2 pi, it's negative. And I know between 2 pi and 3 pi, it's positive. Okay? So this tells me that my graph is concave up. F is concave up when f double prime is positive. That happens from 0 to pi, and it also happens from 2 pi to 3 pi. Okay? It's concave down. when f double prime is negative. Okay, that happens from pi to 2 pi. What do we call it when the graph is switching concavity, when it's changing sign for the second derivative? We talked about this yesterday. Inflection point. Inflection point. Okay, so these points here are inflection points, inflection points, inflection points. Okay, any questions at all about number 9 in all of its glory? Yes. Okay, now that is an excellent question. Excellent question. So this is not the graph of f of x. This is the graph of f double prime. When we're talking about concavity, we're talking about the original function we have way back here is going to be concave up. So yeah, you're right. This graph is concave down here. That's not what we're interested in. We're interested in the original graph. So in a second here, what I'll do is I'll graph it in Desmos. We can take a look at what that original function looks like and kind of compare it to what we got. Okay? So let's look at, see the problem I showed you before, the linear algebra, it looked complicated, but did it look worse than that? I mean, that is a lot of math that's on there, right? Let's do this. And ask me what? Do it. Yeah. What's you would write the inflection, there is an inflection point at x equals pi and x equals 2 pi. You kind of treat it like, how would you write down a critical number? You would say there are critical numbers at pi over 3, 5 pi over 3. Yep. Yep. Okay. So this is what takes time to like get through, not just a 1 or 2 day experience, right? So first derivative, when we're talking first derivative, we're talking about increasing, decreasing, relative max, relative min, critical numbers. These are words that are associated with the first derivative. The second derivative, concave up, concave down, inflection points. That's second derivative talk. Yeah? Yeah. Okay. Let's look at the graph of this and see what actually happens, right? So if we go and we graph this, okay, if we go and we graph it, we've got f of x equals x minus 2 sine of x. Okay, now we wanted to graph this from 0 to 3 pi. Okay, this is what the graph looks like from 0 to 3 pi. It's like what if you had me for physics second hour today, this is what I said we should be doing throughout the year, right? We have a wave and it's going up as we go. So on here, we look at the minimum point. The minimum point is at pi over 3. Is that what we predicted? Yep. Okay. It's got a maximum point at 5 pi over 3, and it's got a minimum at 7 pi over 3. Okay. When I look back at my screen here, that's what I predicted. Minimum, minimum, maximum. Right? It came true. It was real. Okay. Now, if I think about where my graph is concave up or concave down, is it concave up at the start? Does that look like concave up? Yeah. And then is there some point in here where it switches? Yeah. Do you think pi is a reasonable guess? I don't know. Let's see. Okay. Pi, f of pi. That's that point. Does that look like a reasonable location where it could have switched from concave up to concave down? Absolutely. Okay. Here it's concave down, and then it switches to concave up. Okay, we're saying that happens at 2 pi, f of 2 pi. Okay, an inflection point is where that graph turns and it changes concavity. This is what it looks like as a graph. Okay, I'm going to tell you, number 9 is a lot of work. We just spent 19 minutes and 36 seconds going over that there. Okay, going back here.